Okay, it is about 1 o'clock, October 25th. We can begin. So last week, what we went over was we were introduced to more complicated functions, whereas up until now, we used functions in lines. So we have our standard function b plus mx, which described a line. And we can see that it's a line because the x, at least in this function, is raised to the power of 1. What we went over last time was that we began to use functions such as fx would equal b plus mx squared. And we, by doing this, drew out a function like this. And we did it even though we weren't quite sure what it may have looked like initially. We were able to draw out a chart and labeled the values of x and y at certain points, such as -2, -1, 0, 1, and 2. Furthermore, we noticed that due to the nature of the x value of the x function, that because it is raised to the power of 2, it will have the same positivity in the left side of the y-axis as it does on the right side of the y-axis. And we said that we can infer from the way that the exponents work that all functions, whereas the x is raised to the power of an even value, such as 2 and 4, will be positive on both sides. Very well, Mrs. Tiani. Also, we inferred that when we raise x to the power of odd exponents such as 1, 3, 5, etc., the x will be negative on the left side of the y-axis. We refer to these as even and odd functions because of the even or odd quality of the quantity that x is raised to the power of the exponent. Later on, we got a little confused on how to solve or how to draw a function that looked like something like fx is equal to, I believe it was x squared minus 2x plus 1. And the reason why we had difficulty with it was that we did not know the concept that we needed to factor out this function. And by doing so, then we can find what the function should look like on the graph. So if we remember, there are a few components to a function. Some important information we should know. I will leave. So we can leave our function up here, x squared minus 2x plus 1 plus 1. There are a few important pieces of information about a function. There is the there is the y-intercept. The x-intercepts, or as we call them, the zeros. Oops. And as we go forward, we will be referring to them mainly as zeros, merely to save time. No. Zeros, there is the gradient, which, if you remember, will be our m, which applies to the x value. And then there are further pieces of information, such as shape, domain, range, and so forth, but we don't need to know about that at the moment. We'll continue with that later. But using this information, or rather, we should know the shape. Using this information, we should be able to find out what this will look like on the graph. Now, some important things that we know is that we know what the shape is because x to the power of 2, whereas this is the leading term, because if you had plus x to the power of 3 or minus x to the power of 3, it would completely change the function entirely. We know that because the leading term is x to the power of 2, that this should be a parabola. If you remember, a parabola is what we went over last time, the U shape. What we know is that we know the shape. To find these other ideas, we want to write the kind of standard notation for the function. So we need our need a little room. So our function will be fx equals y-intercept plus the gradient times our term, which is x squared. This is what it should look like. Now, if we want to change this standard function to so that it tells us what information we are looking for, such as the gradient, the y-intercept, the zeros, and the y-intercept, we need to adjust this equation so that if you remember when we reviewed position, we need to bring the terms of the y-intercept and the x-intercept inside the variable. So because this b represents the y-intercept and this function is essentially y, we want to write it as y minus b, such that b tells us what the y-intercept is, equals the gradient times x minus a, where a will be the x-intercept. It must be inside the x, which means that the a gets squared also. This describes all of the information we need: the y-intercept, the gradient, and the x-intercept, the zeros. This is how you write out your standard notation of your function so that you have an idea of how the function should go. So this means that y minus b equals m times x minus a quantity squared should translate into fx equals this. So it should be, yeah, we have it here. So there's something important we should realize here, that x is squared. There's some stuff behind it, but the idea is that x is squared. What this means is that if the terms were correct, you could multiply certain terms so that it will still come out to be x squared, and it would represent different zeros along the function. What do I mean by that? As you see, our notation is y in its y-intercept equals m times x minus a zeros squared. This would represent a function where the zeros would be only at one point, because we only write one here, and because it is squared, it is the same zeros. But what happens if you have a function that looks something like, it's poorly drawn. That looks something like, goodness. That looks something like this. We define our x-intercept, the zeros, to be points on the x-axis where x can be 0, or where y is 0 and x is a certain amount. As we drew it here, we can see that if we have our parabola so that it is somewhere where the bottom is below the line and the lines stick up, that there can be multiple zeros for x. The reason why is because our x is squared, which means that the way we have it so that x is subtracted by its 0 in the spot, and it must come out to be x squared, we can have it so that if this was a1 at this point here, and this x value was a2, the equation of this parabola would look something like this: y minus some y-intercept equals the gradient. But because there are two zeros, there would have to be 1 0, x minus a1, times x minus a2. And this would show that there are multiple zeros. But notice that with the way the parabola is, you cannot have more than two zeros. You can have 1 0, or you could even have no zeros if the parabola goes this way, because this parabola will never hit the x-axis. So the equation of this would simply be y minus some y-intercept equals m. And because there are no x-intercepts, it would just be x squared. Now, there is something that we can infer from this. If we can write a function such that there are 2 zeros for x because it is x to the power of 2, that means that in other functions, such as fx equals b plus mx cubed, what's stopping us from simply saying that y minus b equals m times x minus a1, x minus a2, x minus a3, and so forth? The answer is nothing. Nothing stops us from saying this. And the reason why is that this is one of the main ways that functions work. Here. Let me rewrite this. So x minus a1, so sum 0, x minus a2, so another 0, and x minus a3. If our function has an x to the power of 3, then we could write a function, let's say this, that says that this function has a y-intercept at this, a gradient of this, and 3 zeros of these. We can write it this way. The reason why is that this is how our functions work. We don't have to see if a function like this can exist. We can simply plug in the function 3 zeros, a gradient and a y-intercept, and the function will exist. This is how the math works. Because what we could then do is we could say that this is our information, and then we do the equation, and then we come out to a y equals something, and then we can just plug in the x and y values as it is. Now, does that mean that it is necessary to have 3 zeros for this function? No, because because functions functions can, such as this parabola, be high or low on the axis such that they don't interact with the x-axis at all. However, this is not true for all functions. So some functions, they will either go up forever in both directions, or they will go up and down forever for both ways. Because we said before that even functions such as this, because on the right and left side of the y-axis, they can go positive forever. They're the same on both sides. We said that odd functions such as this, while they can be positive on the right side of the y-axis, they would have to be negative on the left side of the y-axis. So they oppose each other, and because they oppose each other in that way, a power 3 function must have at least one x-intercept in this case. So that is information that we have to understand ourselves. So if we were to write a function where it would be a function that doesn't have a 0 in the x, at least that we drew, there would still be an x-intercept at the origin, because let's say we write y minus b equals x squared, or x to the x cubed. mx cubed, what will happen is that this equation is the same as saying y minus b equals m times x minus 0 cubed. Or if we were to say merely y equals mx cubed, that would come out to x minus 0 cubed. So functions such as this one are guaranteed to have a 0 at some point because they differ in which direction they go in forever. That's what the zeros would be. In this case, where we have y minus b equals m this, it will either be true that the x will interact with the 0 at this, or what will end up happening is that we can bring the y-intercept over to the other side. So y equals m x cubed plus b. There are equations out there that can justify turning this into some complicated function that does describe where x has zeros. So it might be a cube of some kind, or it might be x minus a squared and x minus b, something along those lines. So let's go back to what we were talking about before. That was merely extending into other more complicated functions. We're trying to find what this function will look like. So we note that a function such as a parabola can have two zeros if we were to write it this way. It could also have a y-intercept such as this. Now, the way that a 0 works, if we recall, is that a 0 describes x when y equals 0. That is how we found the zeros so far when we did our line functions. And in the exact same way, we will need to plug in 0 for the y here. What this means is that as we have it here, y minus b equals m the x squared and such, we would be left with zero. I'll just write it here. 0 minus b equals m and all of that. So that means we're stuck with a negative b on this side. What happens here is that normally when we describe our function in its standard, this is how we would write it out in finale to show as much information as possible. But when we are trying to find information such as this, we will need to take this y-intercept and bring it over. And what this describes is that we're finding the 0, literally the 0, and the y-intercept affects what the zeros will be in some respect. That's why when y equals 0, this b is still left over, and the b will change the calculation in a way. So 0 equals m x minus a1 x minus a2 plus b. So now we need to figure out what we do from here, because we are looking for the zeros. This is our function right here. This is what we know. So we know that we can find the zeros from this, and the y-intercept changes how this works, but is not necessarily this one. We'll see how that works later. Give me a second. So we should pay attention to these factors. We know that when we multiply these two terms together, it will eventually get to this. But what we can tell is that this leading term tells us a lot about the function. Specifically, we can see that it is x to the power of 2, but specifically 1x to the power of 2. This is very important because the way that we have it, our function, or the way that we have our equation to find the zeros, we have x minus some term times x minus another term. If you remember distribution, what will happen is FOIL. This is an important concept. This is simply the idea that you use when you see 2 times x plus 1. It is the same idea, because what you do is that you take the 2 and you multiply it to both terms. So you multiply 2 times x plus 2 times 1. So you get 2x plus 2. What we have here is the same idea, because we have x minus a1 times x minus a2. Both x and a1 are being multiplied into x minus a2. This is how distribution works. I'm not quite sure if you were taught this before, but there is a rule where like terms can only be added to each other. So if you have 3y plus 3x, you can't add these together to make 6xy. This does not work because these are multiplied together. If you think about what concept this is, what this is saying is that we have 3 y's, and then we're trying to add 3 x's to them. In the end, we can't say that we have y, x, x, x. We can't say that we have 6yx, because this would be saying that we have 6 of yx, 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 yx. That's not how it works. This is correct. We have y, x, x, x. If you were to put everything together, this is true. But we do not say that it is not, let's say, 3xy or whatever. What this is saying is that the coefficients of 3 are merely describing how much of something there is. So when we have, let's say I have 2 markers here and 2 pencils here, we say 2 markers and 2 pencils. So 2 markers plus 2 pencils. We do not say 4 marker pencils or 2 marker pencils. So this is the most simplified version of saying 3y plus 3x. If we were to continue that to this idea of x minus a1 to x minus a2, we say that it is x amount of x minus a2 because x is being multiplied to x minus a2 minus a1 amount of x minus a2. This is also correct. This is a correct way of saying this. This is how this applies to that. This is called FOIL. So it's very important. Now, FOIL describes a certain way of doing this concept, and it's in a way that I really kind of don't like, but I'll show it to you. FOIL stands for front, outside, inside, and last. It is merely a way to, it is an acronym that describes how you multiply all four terms together. So you multiply x by the x and the a2, and you multiply the a1 by the x and the a2. FOIL is not a great way to remember this idea because it is merely a tool to help 6th graders or whatever how to remember how to do it. What you want to know is the underlying logic behind how FOIL works, because when you describe x minus 1 times x minus a2, you have x minus a1 amount of x minus a2. So you're saying you have x amount of it minus a amount of it. That is what is going on. So you say, for example, you have 3 minus 2 amount of x. You would say that you have 3x minus 2x. Or you would be saying you have 3 minus 2 amount of x, which is 1x. So if you're describing the amount of something that you have of something, and you are coming out to a single answer, such as 3 minus 2 is 1, these are the 2 different ways of describing it. But by applying this concept to the factorization, we have this come out. So we see that this will come out to, if we do the math out, x times x is x squared. X times negative a2 is negative x times a2. Minus a1, so minus a1 times x is minus x a1, or technically people like to switch it around. So minus a2x and minus a1x, and then minus a1 times minus a2 comes to plus a1 a2. This describes essentially this. This is how parabolas are written. Even y equals x squared. This is a form of this because in this case the zeros are 0. So these two and this would be 0. So 0 times anything is 0. So this would be 0, this would be 0, and this would be 0, which comes out to this. That's what a normal parabola of y equals x squared does. But in a case like this, we have to use this. So what we can do is we can see that we have x squared, and there are two like terms of x here. So we can see on the outside there is a2 and a1 of x. So what we know is that of x, there are, and we can see that there's a common minus sign. So common minus sign. So there is a2 plus a1 amount of x, because minus a2 minus a1 is the same as minus a1 plus a2 of x, and then a1 and a2 are simply the way they are. So this is what's going on. And you can apply this same idea to x to the power of 3, x to the power of 4, etc. for all the zeros. This is what's happening when we are trying to find the zeros. So we want to apply this function to this. So one thing we can see so far is that this is inside here. So this equation is multiplied by m because of the way we've written it. So m times this equation will come out to be this. But as we can see, in this equation, there is only one term of x to the power of 2. And this x to the power of 2 will be the same as this to x to the power of 2. What this means is that if x to the power of 2 is 1 and it's the same as here, that means m has to be multiplied by the 1 to equal 1. So that means m must be 1. Because if m was 2 or 3 or 4 or so forth, we would see that this would be 2 or 3 or 4 x to the power of 2. And we would then understand what the gradient is. But we can see right here that the gradient is 1. So this is the first bit of information that we have confirmed about this. So m equals 1. Now, something important to notice here is that m is positive 1. Because we said earlier that the shape is a parabola, this means that the parabola must be pointing up. That's what we know. Now, so now we know that this is what we're working with, x squared minus a1 plus a2 of x plus a1, a2. So now we're at a point where this is this. So I'm not dividing these two, I'm just comparing them. All right, so what we can see here is that we can directly compare these two equations. So we can see that the x squared terms are the same. The x terms, we have it written so that because there's a minus 2 here, and this is minus a1 plus a2, we can see that because these equations must be the same, that means we can write, based on what we have here, a1 plus a2 equals 2. Because it's a1 plus a2 times x, and this is 2 times x. And both of these are minus signs, so the sign is okay. So a1 plus a2 equals 2. That's what we know. Over here, we have a1, a2. What we can see is that over here, instead of a1, a2, we have 1. So we can say that a1 times a2 equals 1. So now that we have this is enough information to actually solve the problem. As we have it, a1 plus a2 equals 2, a1 times a2 equals 1. So what we can do is we can solve for either of these and come out to a whole answer. So let's say we take a1 and we solve for a1 here. We say that a1 equals 1 over a2. That's what we have written here. And because we can write a1 equals a1 equals 1 over a2, as we have here, because we know this to be true, we can put that in the same equation here. So 1 over a2 plus a2 equals 2. I'll move this to the side a bit. Oh, this is complicated. Before we continue with this, let's go back a little. So let's look at the signage of this. We can see that a1 and a2, when multiplied together, are positive. That's how we did out our little equation here. So a1 and a2 are positive. This means that a1 times a2 must be a positive number, of course. So when we think about it, we have to think that because a1 and a2 are positive together, that means they both must be the same sign, because of the way we have it here. Because if a1 was positive and a2 was negative, then it would be minus, but that does not work in the way we've written it. So it must be either both of them are positive or both of them are negative. And it's important that we see how it is the sign of the middle term, because if we compare the sign of the middle term with the sign of the term at the end, we can say what the signs of the answers should look like, probably. So as we see it here, it is x squared. Let's get rid of this. Minus 2x plus 1. So both of the terms must be the same to be positive. And because it is negative compared to what we have here, because we have negative a1 plus a2, a1 and a2, because they have a negative in front of them already, and negative a1 plus a2 must be negative 2, that means a1 plus a2 must be a positive number. So when you add A1 and A2 together, they are positive. And when you have A1 times A2, they are also positive. This is something important to know because A1 and A2, they can be either both of them positive or both of them negative, because a negative times a negative is a positive. But what we see here is that because A1 plus A2 is positive, these can't both be negative, because if they were both negative, A1 plus A2, a negative plus a negative, would have come out to be a negative number. So both of these numbers must be positive. That is our takeaway. So A1 and A2 are positive. Okay, that's important to know later on. Now, something we can see here is that A1 times A2 equals 1. We can ignore this for just now. When we see A1 plus times A2 equals 1, we that's very telling because 1 does not have very many whole factors. Because anything times 1 is itself, and we're trying to multiply two numbers together to equal 1, that means we could, let's say that A1 times A1 and A2 are either both 1 or opposite fractions. And what I mean by that is that if A1 and A2 multiplied by each other equal 1, then that means that you would have to have a fraction, let's say 1 over n, times n, because then you would get 1. But we have the constraint A1 plus A2 equals 2, and no number plus a fraction will no number plus a fraction, if they are the opposites of each other, will equal 2. You can only have 1 and 1. So just merely by knowing that, we know that A1 and A2 are our zeros. All right, so that means A1 equals 1 and A2 equals 1. So that is a very long and complicated way to find our zeros. But in the future, most of this will be done in your head because it is a lot more simple than just doing all this. Ms. Tihani, did you have a question? Okay. So we know that our zeros are 1 and 1, and we know that our slope is 1. So that means we need to write our equation x minus 1 times x minus 1 will equal x squared minus 2x plus 1. Let's check it. So we have x times x plus, let's just say, x times negative 1 plus the other x times negative 1 plus negative 1 times negative 1. So negative 1 times negative 1 comes out to 1. X times negative 1 comes out to be negative x for both times. And x times x is x squared. So x squared plus negative x plus negative x plus 1 comes out to be x squared minus 2x plus 1. So that comes out to be this. So merely by knowing our zeros, we already solved the equation. Now we just need to understand B. Now B, it has a tricky little role here. We know that in our equation, we have a 0 at 1. But that's it. That's all we know. And we know that because the zeros are 1 and 1, that means x just has 1, 0, 1. Now, what we do know is that y goes up. The function goes up. And because the gradient m is 0, then that means that just because m is 1, that means that it follows a normal parabola. So if we were to do our chart, we would be able to do it. So we can say that this is what the function should look like. That would be by doing the chart and identifying the points individually. And what we can see is that we can find the y-intercept right here, which is 1. And as you see here, 1 is the y-intercept, which we had at the beginning. Now, the reason why we wouldn't just understand what the y-intercept was in the first place was because if the gradient m was something other than 1, then that means that this number would have been multiplied by the y-intercept as well, which means that we wouldn't have been able to apply this as our y-intercept. Do you have any questions? Ms. Tiani, any questions? Okay. Now there's something a little important here. that might look a little confusing is this, the way it's written, kind of differs from how from the way that the equation might work here. So the idea is that you would write the equation as y minus b equals m times x minus a squared. This doesn't really work here. The reason why is that the equation is x squared minus 2x plus 1, and we said that 1 is the y-intercept. If we have y minus 1 for our equation, it would come out to be m times x squared minus 2x. So this is a little different from how I described it, where we would keep the y-intercept in here. And the reason why is because the y-intercept changes the zeros of the x. So in this case, we would actually not write it this way. So in a sense, that was a little confusing, but the way that it is right is such that you have the y-intercept, but inside of the x value, you have the x factors. So these are the x functions themselves. So that's why you put the x's inside the m, because these are the x ones, and the y-intercept is outside of them, and then you put the y-intercept inside of it, and that's what you have the normal equation for. And you can see that if the m was, let's say, 2, so you had y equals 2 times x squared minus 2x, for example, and there was 1 on the outside, then the 1 would need to be multiplied by 2 so we could put it in here. So it would be, or not multiplied by 2, it'd have to be halved so that the equation is equal. So it would be 2 times x squared minus 2x plus 1 half. That would be an example of how the m being different would mess up how the y-intercept works. But this is how you would technically write it, and the way it is written right here wouldn't be useful enough information to understand what the x's, what the zeros would be, as opposed to how a regular line works. This is what you want to. So this is how you'd want to write it normally, because you have the y-intercept in here, and you can immediately look at it and figure out what the zeros are, and modify it with the m if there's an m. That's a bit more complicated of an explanation than it really needs to be, because I'm not going to really give you that kind of difficult concepts to understand in terms of like the work I give you, at least. But as of right now, we just want to make this process shorter so that it is easier to figure out quickly when you're doing a test on something. So we'll take a little break now, and when we come back, I'll show you how to do it the quicker way, rather than I'm showing you right now the really technical concepts behind what's happening. Does that sound good? We'll take a 5-minute break until 2:05 roughly. Okay. Ms. Tiani, are you there? Okay. So that was all the way that it kind of works behind the concepts. Now I'll show you like the easy way of doing it. Let's have our function y equals x squared plus x minus 6. 1x to be precise. So we can generally understand how to get the function. So all we need to know is that because it's x squared, it is a parabola. Because there's no because there's a 1 in front of the x, we can tell that the y-intercept is minus 6. Okay. So we know this off the bat because we can check m equals 1. Therefore, y equals negative 6, because if you remember, it is y equals m, the x values, which in this case is x squared plus x, and then the y-intercept is on the outside. B. So the y-intercept is on the outside. Because m is 1, we can tell that negative 6 is the y-intercept. So we have the y-intercept, we have the gradient, and we know that it's a parabola. So all we need to do is find the zeros. So the way to find the zeros in the easiest way is to recognize that the 0 is when y equals 1. Y equals 0. So it is x squared plus 1x minus 6 equals 0. So what happens is that this will eventually look like x minus a1, x minus a2 will equal 0. What we see here is that a1 and a2 must be factors of minus 6, because minus a1 times minus a2 is equal to 6. Or just leave that as positive. So a1 times a2 must equal 6, negative 6. That's what we know. So these must be factors in a sense. And what we also know is that a1 plus a2 must equal 1. Now, if we look at the signs, we see that it is minus 6. What this means is that because a1 times a2 equals minus 6, one of them must be positive and one of them must be negative. So either a1 or a2 will be negative. Let's say that a2 is negative, just for simplicity's sake. A1 plus A2 must equal 1. So what we do is that we want to start by thinking about the factors of 6, because A1 and A2 must be factors of 6. There is an exception, which is something that we will review later, but I have made this equation simple. So what are the factors of 6, Ms. Tiani? Can you list some in the chat? And I believe there is one more. Very good. So you have 1, 2, 3, and 6. So let's say that A2 is negative. What we know is that one of these factors minus the other factors is equal to 1. And the factors together must be multiplied to equal 6. So what we do is that we have to look at the factors and we have to put them in pairs. So we have 1 times 6 and we have 2 times 3. What we're looking for is, because one of these is negative, we're finding the difference between A1 and A2. So, Mrs. Tihani, which of these two pairs has a difference of 1? Are they not very visible? So we have our factors and we put them into pairs. So these factors satisfy the condition that A1 times A2 equals -6. So because, yep, second pair, 2 times 3. 2 times 3 equals equals 6, and the difference between them is 1. So we know that one of them is negative, so that satisfies -6. So we need to know which one is negative. Well, we know that the difference between them must be positive. So that means that the negative one should be the smaller one, because the difference between them must be positive. So if it was 2 minus 3, then it would be -1. So it must be 3 and -2 to equal 1. So A1, so we have 3 and -2. So these are what we have inside of here. These are not necessarily A1 and A2. Well, they are, but what am I looking for? Here, I'll just show you. So we got 3 and -2. So A1 and A2 are 3 and -2. Let's write it out. So we'll say A1 is 3, A2 is -2. So we plug it in and we have x minus A1 is 3, and then x minus -2 equals 0. So the x minus 3 times x plus 2 equals 0. And what happens here is that we visibly see right here, this explains the zeros, because what happens is when we apply our zeros, we say x is either -2 or 3. What will happen is that one of these will equal 0. So if x was 3, this would be 0 times 3 plus 2 is 5. So this would be 0. And likewise. So what happens is that if you get this as your, if you find this, then you need to remember that the zeros are the opposite of this. So instead of -3, it would be 3, because you are solving for x minus 3 equals 0. So x will equal 3. And subsequently, x plus 2 will equal 0. So x will be -2. Does that make sense, Mrs. Tiani? Okay. So that's the quick way of doing it. Now, if we have an equation y equals x plus 1, or no, x squared plus 1, we can find the y-intercept, and we'll say that is mx. So y minus 1 equals x squared. We know this is our y-intercept, but the thing is, x squared plus 1, if we were to try to find the zeros of y equals x squared plus 1, we would have to try and factor this. The thing is that we can't factor it. And that's how we know that this does not have zeros, because there is no way to factor this. Because we know that the roots of the factors of 1 are 1 and 1. And we know that the m is positive 1. So this would be 1, 1, and x squared has no 1 in front of it. So these would be the only possible zeros to test for, because these are the only factors of 1, and negative 1, negative 1. The problem is that if we were to say that these were our zeros, we would write x minus 1 or x plus 1 squared. But when we solve for these, it is x minus 2, x squared minus 2x plus 1, and x squared plus x, 2x plus 1. The problem is this is not our equation, so these don't work. There is a way of, there are certain circumstances where doing this FOIL method doesn't really work. Give me a quick second. That should be good. So let's say x squared x squared plus 5x plus 1. That should work, yeah. X squared plus 5x plus 1. This doesn't work because you can't factor it. But what if I were to tell you that this was a function? The problem is we can't FOIL it. But what we can do is we can apply a certain other method. There's a certain other method called the quadratic formula. Now, what this does is that this is a complicated formula that tells us what the zeros of a function to the power of 2 would be. Most functions that you'll have to realistically deal with are parabolas. So the quadratic formula is what you'll really need only. There are other formulas that describe for powers of 3 and so forth, but they're really complicated and you don't really use them that much. But this you do use. The quadratic formula is minus b plus minus the square root of b squared minus 4ac over 2c. No, 2c. I think it's 2a. Let me check. Just making sure that I don't teach you the wrong thing. Yeah, it's 2a. So the way you get this formula is a complicated process while understanding how the zeros in these functions work. But this is what you mainly need to know. If you can memorize this function, then you can just get the zeros without doing too much work. So the A, B, and C in this represents the coefficients of the terms. So you have A, B, C. So AX squared plus BX plus C. That's what's happening. And when you take the coefficients A, B, C, and you plug them into this equation, it'll tell you what the zeros are. Notice that there's a plus and minus here. That is because that, remember, a parabola can have two zeros. So if you plug it into this equation, it'll tell you that there will be two answers oftentimes. And those two answers will be the zeros. So minus b plus minus the square root of b squared minus 4ac over 2a. As we can see here, our a is 1, our b is 5, and our c is 1. So c, b, a. Put that there for simplicity's sake. So a, b, c, we have it right here. All we need to do is plug it into this formula. So the opposite of our b is 5 plus minus the square root of our b is 5 squared minus 4 times our a is 1, and then our b is 5, our c is 1 over all of it 2 times our a is 1. Now, for simplicity's sake, I'll just do it quickly. So it is minus 5 plus minus the square root of 21 over 2. This will be our answer. Let me write it a little clearer. So minus 5 plus minus the square root of 21 all over 2. So if we put those zeros into a little bracket, we would say minus 5 plus the square root of 21 over all over 2, and the square and negative 5 minus the square root of 21 over 2. So this would be roughly square root of 21 is about 4, a little bit more than 4, maybe 5. So 5 over 2 and negative 5 over 2 is about here. So I think it's about here. So 1, 2, 3, 4. Here's one of the zeros, and 1, 2, 3, 4. So it all comes to be like this. And conveniently, it also tells you where in the x-axis that the center of the parabola is, because you are adding and subtracting this square root of 21. You can see that it is -5 plus minus this, that it would be -5/2, which is about here, which would actually be the center. I don't know that this is actually, I don't know if it's actually the y-intercept is here, but it is about a rough estimation. If we were to attempt to understand where the y-intercept is, we would have to find it where we can generally see that it might be around here. Because we know that the in the equation, it always goes up. Oh, wait. Hold on. Okay, I'm right. Square root of 24. Okay, so it wouldn't be all the way up there. It would be like that. So yeah, as we said before, it is y-intercept is 1. Yeah, I don't know why I doubted it. So yeah, we know that our y-intercept is at 1. We know that our zeros are like that. Oh, it's -2. That's why. It's over 2. So yeah, and these are our zeros. Okay, does this make sense? That is roughly how it works. So from this, okay. So if anyone watching this doesn't really understand it later on, you can contact me and I'll do my best to re-explain it. So I think now would be a decent time to start talking about domain and range. Domain, continuity. Domain, continuity, and range. Ms. Tiani, have you heard of either of these before? Okay, domain and range, good. So continuity is something that we can get really quickly. So continuity, if you look, the word looks like continue, and it looks a little bit like infinity. In something infinity-ish. So it continues. It continues to infinity. What this means is that as long as the function is continuous, the function doesn't have any gaps in it. So let's say you had a function that looked like this. If you see, there's a little gap here. Because there's a gap, the function isn't continuous. Because if you were over here, let's say, and you wanted to go this way, the function would have to continue to infinity. So if you look, we travel and there's a break, so it doesn't continue. So in this gap, the function is not continuous. Anywhere else that does not have a gap is considered continuous. That's simply it. So if there's a gap, it's not continuous. That's all you need to know. Every single function that we've gone over so far is continuous. Now, domain in normal terms the word domain is often used to describe the amount of let's say land or property but typically land. So when you say a domain, if you have a domain, that would be like your room. Your room is your domain. Similarly, domain in a function refers to across all of the places that the function goes to. So that is the domain of the function. So if you have a function like a normal one, go back to our line. In math, domain refers to for all x values. All x values the function has. So earlier when we were able to build a chart, you can take a chart and you can plot it for any value across all the x values. So it continues all the way to negative infinity in the x and all the way to negative infinity to positive infinity in the positive x direction. So because the function continues forever and it has an x value for it has a y value for every x on the x-axis, it has a domain. It has domain of negative infinity to positive infinity. So that's domain. One function we've gone over that defies this is the square root of x. So y equals the positive square root of x looks like this. So it starts at 0 and it goes on. So it's like a ray. Because it starts at 0 and it doesn't go to the negatives, because the square root of a negative number does not exist, that means it does not have domain in the negative, among negative x values. So that means that its domain of 0 to infinity. All right, it has no x values in the negative x direction, but it does go on forever positively. Now there's something important here we want to notice, that when we write the domain as it is here, we wrote a bracket for the 0, but for the infinities, we wrote parentheses. There's a reason why. Because we know that the very last x value towards the left that the positive square root of x falls under is 0. We say that that is the very last value, and we know what that value is. So, and the x does have a value there. We write that this bracket represents that the x does reach 0. But with parentheses, parentheses show that x does not reach the value that we're specifying. So for infinity, a function can approach infinity forever, but a function can never be infinity because it can only approach it. Because it approaches infinity forever, but it never touches infinity, that means we write a parentheses because it's not quite infinity, but it's close enough. It extends to infinity. That's how we write that it goes on forever. Range is almost the exact same idea. Range is the x version of, is the y version of what we're talking about. So in other words, you could say the domain of the y. So the range describes the range of values that, that the function can produce. Range of values function can be. So if we look at this line, for example, we see that this line, it goes up forever and it goes down forever across all the x values. So that's why we said that the domain was negative infinity to positive infinity, because it goes to the left and right forever. As it goes to the left and right forever, it goes up and down forever. And because it goes up and down forever and the line is always continuous, that means the range is from the range is also from negative infinity to infinity. If we once again look at y equals the positive square root of x, we see that the range of values it can produce is from x at 0 to forever in the x direction. The square root of x, it technically decreasingly increases over time. So as it goes up over time, it goes, it raises a little less and less, but it continues to go up forever. So because it goes up forever, it will go to infinity. So the range of the positive square root of x is, once again, bracket 0 to infinity, because the y value can go up forever and the x can go in that direction forever. If we compare this to y equals x squared, remember that the positive square root of x, y equals the positive square root of x, is the inverse of y equals x squared. That's how we found the positive square root of x in the first place. We can see that the y equals x squared, it starts at 0 and it goes up forever. So what we do know is that the range of the y equals x squared is that it's always positive and it goes up forever. And the range of it is 0 to infinity. And we can see that the domain of the function is negative infinity to positive infinity, because it goes to the left forever in this direction, the right forever in this direction. But what we do notice is that it's because it goes in this direction forever, because we can apply these x values forever and it'll still come out to an answer. When we inverse it, what we did is that we found that the function looks like this because it was positive and negative square root, but it did not pass the vertical line test, and because it had multiple y values for a point in x, that means it wasn't a function, so we needed to make it only the positive square root of x. So that is the difference between the square root of x positive and the x squared. So that's a very simple version of domain and range. And domain and range have to be the easiest ones of all the information that we need for a function. Because now we know we know what the domain is, the range is, the continuity, we know about the continuity, we know about the y-intercept, the x-intercept, the gradient m, and the shape. And many of these go hand in hand. This is essentially all the information you need to understand a function. So let's quickly look at a function. So if we had y equals 2x plus 4. Mrs. Tihani, what shape is this function? what will this function look like on the graph? It would be straight. Yes, it is a line. It is x to the power of 1. This is the only x term, and it is x to the power of 1, so we know it's a line. So the shape is a line. And from this, we already have a lot of information because we know that a line is continuous. We know that its range is from -infinity to infinity. And we know that its domain is from -infinity to infinity. So we already know that much information. So all we need to do left is find the y-intercept, the x-intercept, and the gradient. Ms. Tihani, do we know what the gradient is? Two, correct. We know the gradient is 2 because our function is the standard. In standard form, it would be y equals b plus mx. So we see we have our x, we substitute in the m. So m is 2, which we found because we can compare. And because we also see it's b plus mx, we have our mx here, and here's our b. So y-intercept is 4. Now, all we would need to do is find what the x-intercept is. And all we need to do is that we know the x-intercept is y equals 0. So when y equals 0, it is 0. It is 0 equals 2x plus 4. So it is x equals -2 because it is -4 divided by 2. And just like that, we already know all the information about our line. We know it goes forever. We know its gradient is 2. We know that its y-intercept is 4. X-intercept is -2 and goes on forever. So there we go. We can see all of the information that we said on our graph. All of this information is told on our graph here because here we have our x-intercept, here we have our y-intercept. These arrows tell us that it goes forever in these directions. And this arrow goes in the -x direction and the -y direction. So we know that it goes forever in the -x and -y direction. And same thing here for +x and +y. So this shows us our domain and range. We can see our x-intercept and y-intercept on the graph. We can see it's continuous because we don't mark on the graph any gaps in the function. So because it is a straight line and it is not indicated anywhere on the arrows or anywhere in the line that it ever stops anywhere, we know that it's continuous forever. And for the gradient, we can see that the x-intercept and the y-intercept here make a triangle, and we can find the gradient by finding the sides of this triangle, 2 and 4. That is the gradient. So for every 2, it goes over and increases by 4. That is our gradient. So all of this information we can see on this line here. And later on, we can also apply all this information to more complicated graphs like x squared and the square root of x. And next time we can do 1 over x. We can do 1 over x right now. Yeah, I'll do it very quickly just to show it, but I'll probably review it next time too. So if we have our graph, y and x, if we have y equals 1 over x, this is what we have to deal with. So 1 over x, when you have 1 over something, this thing in the bottom, the denominator, is, instead of writing divided by, we can say it is x to the power of -1. When you have an exponent negative, it means that it is divided by. And if it's -2, then it'd be 1 over x squared, for example. But we just have y equals x to -1. Now, if we were to try and put this on our graph, we would need to understand a few things about it. So this is our function. One of the things that we went over was domain. So domain. So domain describes all of the places that this function can be. So all the values we can plug into it. Now 1 over x, we can put in all negative numbers and all positive numbers because that would just be all the fractions. But we cannot put in 0 because 1 over 0 is bad. It breaks the equation. You can't have 1 over 0. So because you cannot have 1 over 0, we say the domain is -infinity to 0. And notice that we put 0 parentheses because it doesn't touch 0. And the way that we express that there are two different domains outside of 0 that is n equal to 0 is that we write union 0 to infinity. If you remember, union is from when we did sets, because our domain describes two sets of numbers that can be plugged into x. So this is sets coming back to us. So -infinity to 0, union of 0 to infinity. So that means both. Or for the domain, you could just state that x is n equal to 0, and that would also work. This would probably work better. So our domain is x is not 0. So when we want to say that x cannot be 0, we draw something on the graph to represent that it can't be 0. I think I'll have to do that next time. But just keep that in mind. Our range is also decently easy to find. We can see that our range, by just plugging in 1, 2, 3 further, that we can get all of the fractions. So we know that all the fractions are in our range because we can count 1, 2, 3. If it's a fraction, we put it in. Now, to get whole numbers, what we can do is that we know from before that when we do 1 over a fraction, that means we keep changing, flip it. So we keep the 1, we change the 1/2, so it's multiplied by 2 over 1. So that would be 2. And we can do this for all of the whole numbers because for x, we can substitute in all the fractions and get every whole number that we want, or every number. So because of that, we can get all of the all fractions and all whole numbers. The only thing we cannot get is 0 because we can approach 0 because the larger the denominator is, the closer it is to 0. But I think we reviewed this before. We can count forever and the value will always get smaller. But to get 0, we would have to count to infinity. 1 over infinity would then be 0. But the problem is we cannot count to infinity. We listed that in our domain. We never reach infinity because infinity is too far. So we can never, ever get the function to be 0, but it'll always approach 0. So that means our range will be all of the positive and negative numbers that are not 0, similar to the domain. So these are the two constraints that we have. Now, because the range can never be 0 and the domain can never be 0, that means that it has no x or y intercepts because neither the x nor the y can be 0. So that means our function will just be outside of the axis. So if we were to plug in 1, so when x equals 1, y equals 1 as well, we can see here, we know that the function exists in the first quadrant. If we plugged in -1 for x, that means we would get -1 for y. If we plugged it in, we would see that it's in the negative quadrant. So that means that we know that the function is always approaching infinity in the y direction and infinity in the x direction, but it never touches zeros for either. That means it would look like this. And the same concept here goes in that direction and that direction. So in the end, the function looks like that for 1 over x. And that's where I'll leave off for today because I threw a lot. There's a lot in this. All right, any last questions before we go? Okay, very good. Have a great weekend, stay safe. And if anybody is watching this for the recording and has questions, please let me know.